So, and I don't see the number of participants now, yes, but you see.
So, good morning or good afternoon, depending on where you are, and welcome to our webinar. My name is Guido Pautz. I'm the Business Development Manager at Dr. Maisch. This is a joint seminar between Dr. Maisch HPLC and Dr. Konstantin Zaitsev, who is the CEO of Integrated Bioseparation Solutions. Integrated Bioseparation Solutions offer outsourcing, method development, and chromatography training courses. So before we start, I have to do some organizational announcements. First, according to GDPR guidelines, I need to inform you that this webinar will be video recorded and will be posted on YouTube tomorrow. Your names will not be visible to other participants throughout the presentation, but only if you ask questions using your name. So our speaker, Konstantin, allows to ask questions anytime during the presentation, but he asks that you submit these questions in writing. In order to do that, please click at the question and answer icon at the bottom of the screen, and then type your question, and Konstantin will answer it verbally. So with this, I would like to hand over to Konstantin. The title of the presentation is Ion Exchange and Mixed Mode HPLC in Pharma and Food Analysis. All right, let's get started now.
Okay, I'm ready.
You can share your screen and you can present now.
Do you see me? Do you see my screen?
Yes, I see your screen now.
Okay, I can start. Yes?
Can you enlarge it?
Thank you, Guido.
Can you enlarge the screen? Can you
yes, I can, but yes, but I won't see questions online. If it's not a problem, I can make it larger.
No, it's fine. It's fine.
But maybe yes. Maybe I will see questions after the presentation. Okay, so it is better. Yes, I guess.
It's fine, yes. Thank you.
Oh, okay. So, greetings, friends. I'm Konstantin Zaitsev, owner of IBS. We develop HPLC methods and conduct HPLC courses. But I will tell you briefly about our company at the end of the presentation. And right now, I guess I will come straight to the point. First, just a couple of slides on the basics. In my presentation, I will mention different HPLC modes, so I should list them first. You see, there are exclusion modes, size exclusion, and ion exclusion, and absorption modes, namely ion or ion exchange, reverse phase, normal phase, helic, ligand exchange, and charge transfer. Clearer single modes do exist in life, but real-life situations, mixed mode are observed. If one of the modes dominates and another has some minor contribution, such situation can be considered as some particular chromatography type. For example, when ion exchange mode dominates, we call it ion chromatography. So, therefore, in such cases, any selectivity shifts are defined by minor contribution of some minor mode or minor modes. And also, there are situations when it is not quite clear which of the modes dominates, so that are true mixed modes. And slash sign is used in this case to describe them. For example, ion exchange slash reversed phase mode. Mixed modes can be double, triple, and so on. Here you can see a list of possible double modes. If to sum up all frequently used single and mixed modes, we will get a number around 20 or 25 frequently used HPLC approaches. But right now we'll focus on 3 of them, namely ion exchange /RP, ion exchange /Helic, and I will give you one example of RP/ion exclusion mode. In presentation, I will also use such terms as intra and intergroup selectivity. So I should explain them. Good intragroup selectivity means that substances with a similar chemical structures are resolved well. And good intergroup selectivity means that different groups of substances with different chemical structure types are resolved well. These properties are quite correlated. As a rule, better intragroup selectivity means worse intergroup selectivity, and vice versa. Solutions with highest intergroup selectivity are the choice to develop targeted methods for a single analyte in a complex matrix. Solutions with an average inter and average intragroup selectivities are the choice to develop targeted methods for a set of analytes in a quite simple matrix. So let's go back to ion chromatography. Pure ion exchange mode is a typical mode with the highest possible intergroup selectivity and quite low intragroup selectivity. Thus, it's a technique of choice when the task is to determine a single charged analyte in a complex matrix, and therefore to avoid sample preparation, for example. On the slide, you see the examples such separation. The task is to determine phenylephrine in some medical preparation. It's the syrup. So if we exploit reversed phase mode, you see the poor retention of phenylephrine, and the chromatogram is contaminated by xanthan gum. So it's not a problem. The problem is partially solved when you use mixed mode RP and ion exchange mode. You see the retention is better, but separation of the xanthan gum is not signals are not so high, but you see the separation is not very good. And if we switch off reversed phase mode and use only ion exchange mode, it's strong cation exchanger. So what we'll see, the xanthan gum is here, is not retained or a bit retained due to helic mode. But we see phenylephrine well resolved from matrix and with good retention. So next, the flip side of good intergroup selectivity is quite poor intragroup selectivity in ion exchange mode, which means that compounds with similar structures cannot be separated well, or there are some difficulties with their separation. Here you see the typical example: phenylephrine and pseudoephedrine. So from the viewpoint of ion exchange modes, they are not very much different. You see that secondary amine group here and here. So they differ only by see, by the size of ion or organic ion. So you see separation here, but it can be achieved by playing with some solvitation effects. Yeah, it's not very straightforward to separate structures, to separate compounds with very close chemical structures. So let's consider types of ion exchange. Let's call them submodes. There are strong and weak ion exchangers. Weak ion exchangers work in pH range close to neutral. Strong ion exchangers work in broad pH range, but usually they are exploited under acidic or basic conditions. Silica-based materials are compatible with neutral and acidic pH only, and polymeric materials can be used both in basic and acidic conditions. So silica-based ion exchangers usually work in mixed ion exchange / helic mode, and polymeric ion exchangers usually work in mixed ion exchange / reversed phase mode. Ion exchangers may differ also in ion exchange capacity and therefore in retention. Here you can see a separation of test mixture, metronidazole, nicotinic acid, nicotinamide, and pyridoxine on 3 different strong cation exchangers, which differ by ion exchange capacity and therefore retention. Here you can see ion exchanger with the lowest ion exchange capacity and lowest retention. It's ideal, best suited to separate amines with a high charge or strong amines. This one is with an average ion exchange capacity. It's some general purpose stationary phase, and this cation exchanger is with the highest ion exchange capacity. It's the best suited for separating very low, very weak basic compounds. See here, we don't see pyridoxine here. Yes, only metronidazole, nicotinamide. So see, you can choose the stationary phase which you really need according your analytical task. So now let's turn to examples of separations. I just want to illustrate the possibilities of ion exchange chromatography. So you see here, you see the separation of test mixture in different pharmaceutical compounds. They belong to different chemical classes. Salmeterol, rotavirine, phenylhydramine, dextrometorphan, embifidrine, and codeine. You see, the regularity is maybe not very evident, but you see secondary amines have lower retention, and tertiary amines have stronger retention, and bigger molecules have lower retention, and smaller molecules have stronger retention. You see, stronger retention, say, for tertiary amines, such codeine, and secondary amines, for example, but small molecules like embifidrine, the retention is maximum. The retention is minimal. For secondary amines, which possess quite big size of molecules, the retention is the lowest. There is another example. It's water-soluble vitamins, riboflavin, nicotinic acid. nicotinamide and pyridoxine. So the retention, this three compounds are retained according ion exchange mode, and riboflavin is too weak base to be retained here according ion exchange mechanism. So it is retained due to reversed phase. So it's mixed. It's mixed stationary phase. It's not pure ion exchange. An ion exchange / RP in stationary phase. So here's an example of separation of bettings. So it's betting, and this is carnitine, and this is main impurity of carnitine, croton butane. So you see in acidic conditions, bettings, so acidic group is suppressed. So what you have is a quaternary, in fact, quaternary amines. So they're very separated, no problem with the separation of such compounds on strong cation exchangers. What you see here is an isocratic ion exchange separation of 7 antibiotics used for veterinary purposes, namely metronidazole, tyrosine A, tiamulin, tyrosine B, amoxicillin, tetracycline, and lincomycin. What is interesting in this separation is that all these compounds belong to absolutely different chemical classes, and all of them are retained and separated in isocratic conditions because they have one common feature, one amino group. You see metronidazole, tiamulin, silazine here, tetracycline here, amoxicillin here, lincomycin up here. One amino group, one charged amino group in under acidic conditions. So you see, it's a very interesting illustration of group selectivity because the retention doesn't depend on hydrophobicity of bound structure. It's mainly defined only by its charge. Some more examples. Examples of separation of antibiotic drugs. You see also a separation of pleuromethyline antibiotics, separation of penicillin antibiotics. It's tyrosine antibiotics, tyrosine A, B, and some minor ones. Separation of doxycycline, oxytetracycline. Also, it's very interesting that the retention is mainly defined by one amino group in acidic conditions. And also, you see the separation is not, the selectivity of separation is not very high, just because, yes, in this mode, in intragroup selectivity is not very high. You see here tiamulin retains a little bit more because it's tertiary amine, and here valine is primary amine. And also, yes, ampicillin retains more because the size of ion is a little bit small. Citalopram on cation exchange on cation exchanger. So also, so strong cation exchanger can be used to analyze different antipsychotic drugs like citalopram and duloxetine, sertraline, and so on. All these drugs can be easily separated in strong cation exchange mode. Oh, yes. For example, phenyltoluene and codeine in strong cation exchanger. There is some complex medication. No phenyltoluene plus codeine. It's now water soluble vitamin. Oh, it's not. It was strong cation exchange. Absorbance. Now it's weak cation exchange absorbance. Separation of vitamin B1 thiamine. So on the background of ascorbate, folate, and pyridoxine, which do not coalute with thiamine. So thiamine can be determined in complex matrices, which contains another vitamin. The same for ascorbate and folate, vitamin C and B9, but now in anion exchange mode, weak anion exchanger. See here, ascorbate and folate well separated. Analysis time is quite short. And you see another vitamins such as thiamine, pyridoxine are, of course, not even retained, but they are excluded according to an exclusion, so they do not correlate with them. So also ascorbate and folate can be determined in very complex matrices. In weak anion exchange modes, also can use to separate compounds, for example, with one phosphoric group or two carboxylic groups. On weak ion exchangers, the example of valsartan, one of the most highly prescribed medicines for antihypertensive drugs. Valsartan has one carboxylic group and one tetrazole group. So and they have almost the same pKa value, acidity value, around 4, I guess. So such compound with two weak groups or one strong acidic group like sulfonic group or phosphoric group, so maybe also even two of them. So well retained and separated using weak anion exchange adsorbents. So now let's turn to mixed modes. This is example of mixed mode in which helic mode dominates. So and anion exchange here, we can exchange mode in the minor mode. Here you see retention and separation of the three weak carboxylic acids from the viewpoint of a chemist. Biotin, vitamin H, nicotinic acid, vitamin B3, and pantothenic acid, vitamin B5 is just weak carboxylic acids. So they can hardly be retained in pure anion exchange mode, even on strong anion exchanger. Their retention is not very high, and you can do it higher, but resolution becomes not very robust. So I would prefer such helic/weak anion exchange separation. So helic adds retention for them. So you see it's biotin, nicotinic acid, and pantothenic acid added to some premix, and premix for feedstock. So you see that separation is very specific. So different compounds, mostly another vitamins, do not coalute with biotin, nicotinic acid, and pantothenic acid. Oh, you see, I know this vitamin B1, this thiamine, this one. So you see, the resolution, the separation is quite specific. Another example helic mixed mode, a separation in which helic mode dominates. There's a mixture of antihistamines. So mixture of histamines, namely cetirizine, chloramine, phenylphenramine, chlorphenramine, dilortadine, and oxylamine. You see what I call the group, yes, the chemical group with a similar structure. See, their structure is very similar except for cetirizine. They all have one tertiary amine, or here for the secondary amine group, and one pyridine group, pyridine in English, yeah, pyridine group. So except for cetirizine. So, but finally, it works out that it comes out that they can be separated with a very separation is very specific. You see, it's not a mixture of 5 standards. It's a mix of 5 medicines. So, of mixture of 5 dosage forms, different, very complex dosage form. We see other medications are not retained or even excluded, and you see drugs with one amino group, metamizole. Oh, no, metamizole is this complex, dextromethorphan. It's a medication like codeine with one amino group. The retention is a little bit poor. Separation, retention of all these compounds is bigger. It can be they can be. Oh, sorry. They can be separated from neutral compounds, first from acidic compounds, and even from basic compounds with one amino groups. And they are eluted in one window under isocratic conditions. So perfect. So what is the catch? The catch is that specificity of the separation, which is specificity of the separation using cation exchange mode. We separate these compounds from all other intergroup selectivity, and we use helic mode to improve intragroup selectivity and to separate them from each other. So here's the catch. So now about mixed RP/IC cases where mixed RP/IC approaches may be used. You see, these mixed modes are, to my mind, very underestimated in pharmaceutical analysis. So they first can be used to mimic standard pharma compendial methods in order to improve their selectivity and retention. Second, they can be used to replace standard pharma and food methods with ion pairing mode. So because ion pairing chromatography is not very good analytical technique, there are a lot of drawbacks. But historically, there are plenty of ion pairing RP separations in pharmacopoeia, because most pharmacopoeia methods were developed in 80s and 90s. So and that times there were no good ion exchangers, and people were just forced to buy reversed phase columns and using ion pairing technique to prepare ion columns from reversed phase columns. Now it looks It looks a little bit crazy, but there is nothing else to do but just to try use mixed mode, special mixed mode stationary phase to replace those methods anchoring methods. And of course, such calls can be used to develop new farm and food agriculture methods in mixed PIC mode. Here is a couple of examples. First example is separation of caffeine with riboflavin pyridoxine. See, caffeine, vitamin B2, vitamin B6, also under isocratic conditions. So it's also not a mix of standards. It's called non-alcoholic beverage concentrate from dollar. I know that somewhere a lady from dollar is registered on this webinar, so here's a dollar concentrate. So caffeine and two vitamins in a single run. So you see very specific separations of vitamins, etc., sweeteners, what else? Preservatives, colorants, aroma additives are not retained, or you are not retained here, or even excluded. You see only caffeine and two less vitamins. Separation is exceptionally specific and very quick. So another example is separation of catecholamines. I see two stationary phases. We use two different stationary phases. See some that their selectivities are a little bit different, but generally we see good separation of all main catecholamines, norepinephrine, ephedrine, dopamine, and then two more norepinephrine, metanephrine, and also serotonin, the last P. So now, as an example of reverse phase / anion exchange chromatography, you see a separation of benzoic acid, sorbic acid, benzoic acid, sorbic acid, and ascorbic acid in one isocratic ram. So we see sorbate and benzate are well separated, and in reverse phase conditions we will see the unretained ascorbate and yes, and two peaks of sorbate and benzoic acid, benzate here, and unretained ascorbate in void volume. So, and using mixed mode, we can see all the three compounds together near each other and well separated. So as I already, as I promised you, one example of mixed RP ion exclusion mode. So you see, for example, you see ion exclusion mode can be as ion exchange mode also can be combined with different modes like helic and RP. For example, here you see RP/helic separation of sweeteners, yes, of sweeteners, caffeine and preservatives, arabic and benzoic acid. Here, it's not very reverse phase separation. That's why I used /helic here. to underline, it's not very typical reverse phase separation, but it's quite close to the classical repeater. So what if to combine reverse phase with ion exclusion mode? You'll see that acids, namely benzoic and sorbic acid, go to the left here. So 6 here, 6 and 7. You see 6 and 7. Now they are not lost peaks because they are excluded. So here's caffeine, 4, 4. So it is retained according to reversed phase mode, and benzoic and sorbic acids are excluded. So you see benzoic acid is excluded more than sorbic acid because benzoic acid is a stronger acid than sorbic. So you see, now we can, using reverse phase mixed reverse phase ion exclusion mode, we can use the contribution of minor ion exclusion mode to suppress retention of charged acidic or basic compounds in reverse phase mode. So conclusions. I thought a lot about conclusions, but I decided to underline 3 main facts, to my mind, 3 main facts about ion exchange chromatography in food and pharma analysis. First is that the belief that ion exchange chromatography is ineffective for separating organic compounds, including pharmaceuticals, is just a myth. So high quality ion exchange columns, even with high ion exchange capacity under appropriate conditions, provide symmetric and narrow peaks. It's a strong cation exchanger with very high ion exchange capacity. It retains such very weak base like metronidazole. But you see, their efficiency is good and asymmetry factor is quite low. You see nicotinamide, you see asymmetry factor 0.05. So it's this stationary phase, ion exchange stationary phase, provide very high exchange capacity and very high efficient plate count and symmetry of peaks. So also ion exchange HPLC can be used with any detector, any standard detectors, including UV, refractometric index detector, and fluorescent detector. So, and also under appropriate conditions, even a fly scattering detector or MS detector can be used. The second conclusion is that ion exchange chromatography is a technique of choice. And the task is to determine a single charged analyte in a complex matrix with the highest possible specificity and using null sample preparation. So we already talked about. So, and conclusion number 3. So to determine the group of structurally related compounds in a complex matrix, an appropriate mixed RP/IC, or helix/IC mode should be used. And that's it. So now about fields of application. So yes, of course, to my mind, ion exchange chromatography is very underestimated chromatography type for pharma and food analysis. So in pharma, it can be applied for dosage form analysis and drug screening applications and PK, PD studies. In food analysis, analysis of water-soluble vitamins and complex matrices, analysis of preservatives, sweeteners, dyes, and complex matrices, analysis of free amino acids, organic acids, bettings, and food additives, and even charged toxins, for example, biogenic amines can be analyzed with means of ion chromatography. In biotech, first of all, it's analysis of feed solutions, water soluble, vitamins, amino acids, etc. And also peptides, nucleotides, and free bases. They're also charged and can be effectively separated and determined in complex matrices. So, as I promised, a couple of words about us. We are, first of all, our strong point is outsourcing HPLC or HPLC method development, validation, and transfer. First of all, we're specialized in routine methods, development of routine methods. Mostly we rarely use, for example, gradient separations. We're focused on isocratic separations for routine analysis. So we can make HPLC method development. You see here, we can also improve some existing HPLC methods. We can make chiral HPLC methods, some PKPD method development, and even carry out some research work with the use of HPLC, for example, discovery of active compounds and so on. So and also we conduct courses on HPLC and HPLC method development. So if you want to know more, so you are welcome. Please feel free to contact us, ask your questions. Second, you can send us your email and we'll let you know about our next webinar or webinars, and you can share your ideas on relevant webinar topics. It's very interesting for us. So thank you very much for your attention. Guido? Hello, Guido?
Yes, I'm here. I'm still here.
Oh, okay.
Thank you so much for this excellent presentation and this insight into ion exchange and mixed mode chromatography. There were a couple of questions from the audience asking for more detailed information on the eluent conditions and the stationary phases used for the specific examples you've shown. I've answered to them that, of course, a part of what you are showing is, all what you were showing is your work. And so the methods that you develop, that's your intellectual property, and you may or may not be able to show and to share all the information. So to what extent can you share more information? Because some people indeed asked for this presentation in PDF
I see three
format.
questions. I see three questions, and I can answer them.
Yeah, the three questions you see are not answered.
Not and 5 questions are answered. Okay.
Yes.
No problem. Why IPA isopropanol? Yes. No.
Isopropanol, yes.
Isopropanol, maybe. Isopropanol. Okay. Why IPA is preferred as tertiary gradient component at multi-mode column application? Thanks. I don't know. It's a bit. I don't know. I remember that guys from Shimadzu like to use isopropanol almost everywhere. I don't use isopropanol, sorry guys. I don't use it. Why? Because you see, using isopropanol to wash columns is also quite risky, right? Risky trick, because if you, for example, have a new column filled with isopropanol. And if you, for example, use then wash column with water, it's very dangerous to wash column with water or water-rich stationary phase after column filled with isopropanol, or vice versa, to fill the column which is filled by water or water-rich mobile phase with isopropanol, because in these cases something bad, I don't know why, but something bad usually happens with the column. Its packing can be crashed at one moment, in my experience. So I avoid using isopropanol. I use it only in maybe only in, of course, only in normal phase chromatography where it is necessary. Standard mobile phases, like say in isopropanol acetic acid, or dichloromethane is isopropanol acetic acid, and so on. So only in normal phase, only when it is necessary. And as for tertiary gradients, usually I don't use gradients at all, because all my solutions are focused on isochromatic separations, because they're most robust ones. That's why I rarely use gradient, only if it absolutely cannot be avoided. So, is it useful in bioanalytical techniques? Of course. In bioanalytical techniques, so bioanalytical techniques, it's analytical technique. So also all charged compounds, you see, as already mentioned, all peptides, oligonucleotides, nucleotides, free bases, everything can be separated in exchange mode. So, what should be the strategy for mobile phase selection and optimization while using a mixed mode stationary phase, for example, RP/ion exclusion chromatography? Dear participant, please, you're welcome. You're welcome on our HPLC courses and HPLC development. It's very complex questions. And usually it's I spend about half a day to answer this question on HPLC course. Oh, let's say 4 or 5 hours. So it's not very easy to explain on the webinar. So I usually unveil all these topics on HPLC course. So
can you perhaps just explain the choices you have and what properties you can? Yes. What properties you can influence by the choice of your field?
It's not possible to explain on the webinar. So you see, it usually takes me about from 4 to 5 hours, but not as a part of the one integral course to talk about it. It's very complicated topic.
Mm-hmm.
Not even possible to describe this in one sentence or 2 sentences. Sorry, it's so much parameters that can be varied. So let's go to maybe another question. What biopsy element and exactly stationary phase information would be great? The same to all examples, element conditions, and missing stationary phase. So sorry, yes, you can write us and we can prepare an invoice, but it's our intellectual property. So we can make or adapt this method for your samples. Is it useful? Oh, if the phases seem to be interesting. Unfortunately, there's too many information about Alien. Of course, sorry, it's our it's what we do. It's how we earn money. Sorry, guys. So we can develop any method for you, no problem. I must leave now. Oh, but can I get information or not? What should be strategy? Okay, that's all. I guess that's all. No questions.
Okay, I think we have no open questions now. Does anyone else want to ask something? Let's wait a minute or so.
Okay. So I guess no. I guess everything. Maybe it's not. Maybe you see, when there is no questions, there are two. There are two options. The first option is everything clear. The second option is absolutely not interesting. Or yeah, okay. There's third option. So people are thinking about it. So they have an hour or two just to think about it. So it's when I conduct digital courses, sometimes I hear very loud silence. People are thinking. So okay, I see you need some time to think. Coffee break. So coffee break. you need just to think about it. Say about 10 or 15 minutes. And then then people ask questions after. They need some time to think about it. So it's not it's not a problem. Dear participants, it's not a problem. If you have more questions, just write. So sales HPLC done today. No problem. I will answer them.
I see no more questions coming in. You always have a chance to contact Konstantin or myself. I will forward the questions to him then. After this webinar, I see there are no more questions coming in. So let me close the webinar now. Oh, there's one thing now. Okay. Can you see that?
Oh, can I inject potassium hydroxide extract in mixed mode corn? No problem. Just pH of your sample should be the same as in the mobile phase. So you should maybe, I guess, if it's not basic conditions, if it's acidic conditions, you should add some acid, for example. So phosphoric, I don't know. What acid are you going to use? So the pH of sample, the ideal situation, the best situation is that pH of sample is equal to pH of the mobile phase. That's it.
Well, obviously, a 0.6 molar potassium hydroxide would be very
the base.
Yeah. I mean, most of the phases, if not all, you presented today are silica based. So this answer is not limited to mixed mode phases, but to all silica based
yes.
media. And most of these media would not be stable beyond pH 9, some pH 10.
There are different, much more difficulties. Yes, baseline distributions and so on. Not robust separation, baseline distribution, everything. So many bad things can happen because of mismatch of pH of sample into the mobile phase. Yes, very many bad things. So I can even, I have a pen and I can write all the bad things can happen to your separation due to this mismatch of pH. I've already remember not less than 5 or 6 bad things that can happen. So you can just send this question to our email, and I will explain in details what should you get, what bad thing should you get if you inject alkaline solution. So I see also 0.6 mole is quite big load, column overloading, I guess. It's quite big amount. It's quite a big amount, so I guess the sample should be diluted also.
There's a new question here. Did you see that?
Okay, just 1 second. I guess sample should be the page should brought into correspondence with the page of the mobile phase, and I guess you should also dilute the sample. An exchange mode loadability in exchange mode is not very low. On silica based material, the loadability is quite good, but 0.6 moles, I guess it's too much for one single injection. So one more question. Is it possible to work only with TFA water as a trial? What's your experience? Yes, it is possible, but it's not what I usually use, because usually I use UV detector, and TFA is volatile acid. It's good for evaporative light scattering detector or for MS detector. It is not very good for UV detector, because you will get baseline drift, you see disturbances of baseline, and so on and so forth. So that's why I usually use with inorganic buffers, because I usually use UV detector. But it is possible. Of course, it is possible. But you should all take into account that TFA is better to use with of evaporative detectors, including MS. But not for UV detector. I usually use phosphate buffers. So I will unveil some tricks. I usually use phosphate versus sulfuric acid because it's optimal buffer for UV detector. No problem. So you can use, yes, you can use it, but for evaporative detectors, for UV, it's better to use phosphate. Or if you're one more, if you're afraid of precipitation of phosphates in the mobile phase because of high acetonitrile content, you can, for example, use not alkaline phosphates, not potassium or sodium phosphates. You can use, for example, ammonium phosphate. Its solubility is much more than potassium and calcium salts. So, it's, for example, it's not absolutely for piston pump. It's not a problem to use 20 millimole ammonium dihydrogen phosphate buffers when the acetonitrile content is 80%. It's absolutely not a problem. Okay.
All right.
Yeah.
I think we have worked on all the questions.
Okay, and it's not a problem. One more. Okay, one more number. And for example, you can use 50 millimole dihydrogen ammonium phosphate with the acetonitrile content up to 70%. To my mind, up to 70%. It is not a problem for a piston pump. Okay. All secrets are unveiled. Or
I think the person whose question you are answering has already left.
okay? No,
Uh,
maybe it's good. It's interesting for all the participants. Okay. So no questions.
No questions anymore.
Oh, okay.
No, there's one more
Okay,
coming.
great. It's so 1 hour. Great.
So
It's,
thank you, Konstantin,
optimal
once
time for a
again
webinar.
for
Thank
your
you, Guido.
presentation.
Thank you, friends. for your
And I wish
participation.
everyone a good afternoon. Take care and stay
Yeah,
healthy.
take care. Bye. Bye.
Bye.
See you.